please. Respected Silisha and all dear my colleague, I would like to welcome you for this presentation. Today I will be talking about the world of circuit simulation with respect to RF and microwave circuits. I am Pramod. The short introduction about me, my skill set, I am basically a micro circuit designer. I am good at designing an active and passive circuit devices, especially low-noise amplifier, oscillators, mixers, power amplifier, and I'm good at designing the matching circuits and making circuit stabilization and board level tuning, and these are my skill sets. And regarding my qualification, I done my bachelor's in electronics and communication under LABVIEW, and I done my master's in RF communication and done my PhD in electronics engineering under Jain University. I am basically from Bangalore. It is an IT capital and Silicon Valley of India, and it's having a GDP more than $110 billion. So the flow of presentation is the first. I will be talking about what is the motivation to talk on this topic, and followed by that some of the classifications of the models available for the simulators, and I will be talking about what is the computational speed and the logical concepts. Followed by that, I will be describing few famous EDA tools, and I will be talking on my circuits and what kind of a work I will be doing in MMG. I will be discussing, and then I will be summarizing my presentation. If I'm looking at the scope, whenever we have got anything in mind, we have to design any circuit. First, we will be writing on the paper on a blackboard. We will be discussing what should be the input and what should be the output and what kind of work it has to be done. And later on, we will straight away start with the simulation. In a simulation, we will be looking with 3D models, and after that, and if it is an RF and micro simulation, we will be taking with RF and micro simulation. And followed by the simulation, we will be making a machine prototype. It is like fabricating the circuits, where exactly what you have done in a simulation, and then prototype testing and concept approval. If you are looking at these 3 steps here, it depends upon the efficiency of the machine, how it will be fabricating, and this is what kind of a testing method you are using. And this part, the mistake can happen or error can happen up to some 5 to 10%. Most of the mistakes will happen in this simulation world. So, and always you can see that there is a loop. That means if you are looking with in a single time, you may not be end up with a good result. So it is a loop. Every time you want to optimize it and then refabricate it. So if you are looking in depth with the simulation, there will be several steps in the simulation. First, system design and design capture, followed by that analyzing a simulation and performing a layout and verification and extraction. If you are looking with each and every step, there is a connection, and every step, this one is a data file where a designer will be using. This is a netlist every time the tool will be creating. There will be always interaction between a data and discussion between each netlist and a data at every step. So it will not come with an, it is not with a single shot. Every time, if you are not ending with the proper layout, again you have to start with the system design. It is a loop every time. So you will be always working in this loop, and if you made a single mistake, that will be iterative. It will increase your mistakes, and you will end up with a wrong analysis. And basically, I will be classifying the models. If you are looking with electronics, electronic circuits, we will have some time domain measurement, frequency domain measurement, and we will be cumulatively with time and frequency we have got a modulation. If you are looking at the time domain measurement, it is simple. We have got SPICE models. It's very easy, and less expensive tools are available, and Affleck transient is there. This generally for the low frequency we can go with all time domain measurement. Here some of our theoretical concepts like KVL, KCL and circuit node analysis, all those things come into picture here. And if you are looking at the frequency here, frequency domain stays with more with the complex numbers, and we will be having phases. And there is a parameter, important parameter for higher frequency is S parameters for linear, and there is an advanced version of an S parameter. We have got an X parameters, and we have got some of the devices like filters, package interconnects, and some of the linear amplifiers. These are some of the devices which comes with the frequency domain, and these are the models available. They are the micro office linear model and harmonic balance linear model. And cumulatively, there is a common between a time and frequency domain, there is a modulation. If you're looking with the modulation schemes of any of the communication system, you will end up with a lot of exponential equations or trigonometric equations where we require to take care of a lot of harmonics, intermodulation effects, and a lot of nonlinear effects. For that, we have got an harmonic balance methods. Models are available. Basically, it is like steady state numerical analysis. Some of the devices, challenging devices to design are oscillator, mixer, up converter, down converter, and power amplifier. This require a huge experience to design and proper devices. And here we look at it, output it will be voltage, current, and power at node analysis and also port. Here some of the models like ADS is having an harmonic balance models, and AWS is having one more harmonic balance method, and APLAC is the one intelligent model. Out of this, we have got SPIC and APLAC linear transient models. So this can be sometimes and faster, and it will be of less complex compared to this model, but it will not be handling a strong nonlinearity natures. And just I'm classifying the linear simulator mills. It will have like a simple measurement like gain, noise speaker, and some of the circles where you will be playing with a Smith chart. So that kind of a linear analysis can be made with linear simulation. As parameter analysis, it's like small signal analysis for circuits. And harmonic balance means we can handle with non-linearity of the circuits, where we can understand the harmonics effects and intermodulation, dynamic range of the power, everything you can measure, and a special device like power amplifier and mixer. Linear harmonic balance, this one when you are playing with some of the active devices where you want to judge about the biasing point and different DC levels and different current level or internal nodes has to be made, most we can go with a linear harmonic balance method. And HPICE is a simple as just advanced version of a SPICE model. So it can handle some non-linearity design, it can handle some oscillation startup conditions and transient analysis. And this is entirely different word. Most of our in our team, they will be using a lot of electromagnetic simulations. Once you are looking at the EM 3D electromagnetic EM structures, these are some of the microstrip line, these are the connectors. It will be simulating in various advanced techniques. Those who are designing with antenna array, and some of the RF components, filters, high-speed interconnects, so here high-speed interconnects and linear amplifier will go with 3D electromagnetic simulations. And there is a separate one more, is complete 3D analysis, Axiom, EM site, and AC. These are the products available in the market, where it will not only analyze the microstrip geometry and all, it can take the consideration of a packet, parasitic effects. These are the inductors, capacitors, these are wires, and these are the pitch, and we will be having some ICs. So all those consideration will be taken care with this kind of a tool, and it is for system level and also for component level designs. And yes, based on this, I made this major focus on this 3D electromagnetic simulation, because most of our team are working on this. So I have just made a different class. If you are, I made one chart where it will take from 2D to 3D, and based on the computational time, I have classified into basically 3 types. So if you are looking with one type is a simple transmission line concepts will be there. It will have a 2D analysis where this is one just an microstrip line, and this is one coaxial cable. And transmission line concepts it will take, and it will make a cross-sectional solver method is completely 2D, and it is require less computational time. Whenever you are looking whether it's like 3D planar or is 2.5D, we can say that when it looks like 3D, but the evaluation will not be completely 3D. So we have got a concept, mathematical concept like methods of movement and eigen models, where like planar interference, antennas, rectangular cavity, circuits, labor simulation, all those things can be made. This is a 3D planar concept. Once you look at it, this is a completely 3D method, where we will be having a mathematical technique called as an FEM, that is a finite element methods, and we have got finite difference time domain method and boundary element method. Here there we have, if you want to make any of the like filter lines with waveguide structures and all, we have to make it with a 3D analysis properly. If you are preparing a skull, human skull with an phantom model, you want to analyze with electromagnetic things, you want to go with this kind of a pure 3D analysis. This will be provided by Axiom and EM site and AC, and some fast solver techniques are available. And this part I will be again going in quite more explanation. I want to distinguish between for a designer. You have to consider about this 4 techniques. Whenever you are making this one, that is a finite element method, it will go on, it will take any of the microstrip geometry or any kind of a structure, it will divide into a multiple tetrahedron and it will be analyzing. It will apply the Maxwell's differential form equation in the time domain and it will analyze. Whereas this methods of moment, this is available in HFSS. And if you are looking with some of the tools like ADS and AWR for the basic, where it will make it faster, it is 2D solver. You can look at it, the structure has been, and cross-sectionally it has taken with divided into number of elements. It is called methods of moment. It will apply integral form of Maxwell equation in frequency domain. It is faster, but up to and 2 gigahertz or 3 gigahertz you can use this one. You can end up with a good result, no issue. This is basically when you are dealing with lot of complex active circuits and all, we can go for it. Whenever we are having a structure, say about this, we are looking with the electrical characteristics of a car or aeroplane or any of the different geometry in the world, you can go with an FDTD, or the finite difference time domain method. This is completely 3D evaluation. If the structure is taken and it will be evaluation is done with an finite difference time domain, and it will apply the Maxwell's equation in time domain. And this is one more advanced method, the BEM, or the boundary element method. If you are any geometry, they will make it one enclosure. May not be always in a cubicle, it will consider with a spherical, cylindrical. It will create on boundary and it will analyze in a various direction, and this applies with the linear partial difference equation in a time domain, and it will make an analysis. And if you are looking with most of the designers working with the EDA tools, they will complain about the software is slow and it's not working well. I would like to say that when if they are using a dual core i7, it will take a lot of time if you are making with the EM structure simulation, because EM structure simulation the background there will be a lot of netlist will be created, and every time it has to consider with the data file. Lot of things will be complex calculation will be at the background, so it will take around 600 minutes if you are having dual core. This is a system which I am having in my lab, which is having a single node and 6 cores with this frequency. Frequency I am having around 3.2 gigahertz. It will take around 2 hours if you want to simulate with the complex geometric structures. And if you are looking at the machine, 6 node and 6 cores, these are some of the good processor where it can take care of your software very fast. Whatever the software you are using, if you are going with this kind of a machine, it will be better. And sometimes it demands with a bigger RAM if you are looking at like HFSS and all. In a linear simulator, again, I will just say that one, if you are playing with elements with RLC and microstrip geometry partial lines, you can go with the linear simulators. And if you are having devices like filter, coupler, divider, low noise amplifier, and their measurement is only small signal analysis, you can go with the linear simulator. Because this kind of a linear simulator which cannot have any compression point analysis or dynamic range or non-linear characteristics. If you are performing any non-linear characteristic with this kind of a simulator, then you will end up with a wrong result when you come up with a fabricated result. And this is harmonic balance. This is for especially made for and non-linear circuits. You see that one just as a simple picture is saying that you should balance with linear and non-linear circuits. Suppose linear circuits, you are having RLC in your circuit and you are having non-linear characteristics with some transistor and all. You should every time interact and it should perform properly the calculation. So some of the devices like mixer, power amplifier, oscillator, multi-tone simulator, IQ circuits, and high frequency carrier modulator goes with harmonic balance. And there is one more linear for this one. If you are going with some of the linear, you want to make more time domain analysis, then you can go with the linear harmonic balance method, where sometimes it cannot handle with this kind of an issue. Say there is a step recovery diode response, it should not be like this. It was showing a wrong analysis. Sometimes you will be, if you are using a wrong model, so for your analysis with especially semiconductor device, it will end up with a wrong analysis. And this is just advanced version of your SPICE model, SPICE model, where you are looking with the time domain analysis, where you can have not only with some of the matrix, you can have with oscillation startup, and you can have some non-linearities measurements it can tolerate. So it's quite advanced than your SPICE model. And this is a new technique, is the APLAC model. It is very intelligent model, but the problem with this model is the vendor has to be provided an APLAC model for your design. Say about you are designing an amplifier with respect to one Philips company, say an XP Philips with some FET model. So that vendor has to provide this model for your particular tool. Then you can make a good analysis. Or else you should look at the data sheet and you want to change the parameters of existing models like TOM model or any Gunpon model. Any of the existing models, you have to change the second parameters and you can use it. And some of the logical concepts is we have got less time. I have just highlighted this question. If anyone is having any kind of doubts regarding tuning, optimization, and yield, and some errors in a schematic, if you are facing any problem with an answer, we can discuss after my presentation. And just I want to highlight this one. Whenever you are looking with any of the tools, especially like EDA tools, if you are just drag and drop, if you are looking at in a schematic, it looks like this. If you are downloaded in internet, art style will look like this, lines will look like this, and after the drawing is no schematic link, means many times it will show some different color and all. If you are not believing on that tool, means if this interaction between a drawing layer and model layer is not proper, then this GDS file, it will end up with a wrong Gerber file. So there will be, and sometimes there will be bad ideas saying that downloading some models from the internet and directly putting in your design, and if you are not having the proper linkage between model layers and drawing layers, then analysis will be wrong. Even though circuits looks better in your schematic and layout, but then once you fabricate it similarly, you will not be end up with a proper testing prototype. And I like to show some of the famous EDA tools. One of the EDA tool is Helios, which is having a system level and also component level design. It is a specialty of this tool is it is having thermal measurements, power plane, and it is having signal integrity models and power integrity model. It's a special tool where it can have a lot of complex X models are there. It can simulate various geometry structures, and it is having 3D version. It is having a good connection with schematic and layout. And one more is the AWR is also very big good industry. They provide different tools for different kind of elements. They provide a different tool, micro office for especially RFIC, MMIC, monolithic micro integrated circuits, PCB design, module design. They will provide micro office, and VSS they provide for system level design like wireless communication radar system, and they provide analog office. It is for VLS and small, very small structures designs. And if you are looking with Analyst and Axiom, they provide especially for analysis of antenna and synthesis optimization. They have got a different tool. And they provide a different license. And okay, there is one more tool called ANSYS HFSS. This tool has some specialty. There is no geometrical or material complexity, whatever it may be, electrical size, whatever it may be, it can simulate. It can simulate with a micron size of your circuits to aeroplane size. And it can have various structures, simulations with very complex simulation methods, and this is about HFSS. And if you are looking at CST, even this is available in our lab. Even CST and HFSS work with the same kind of an application, but mathematical computing is different. Just I will be highlighting features in upcoming slides. If I am just highlighting key features of HFSS and CST, if HFSS go with finite element method, and this will go with the finite integration method technique. And many times people will say that is more accurate, I am getting good results. Many times they'll say that, and I don't advocate any of the tool. So this is faster because it is making with analysis with the time domain. And if you are looking with HFSS, always deals with mesh and EM analysis with a faster and accurate. And here we will be having multi MRI coil, because it can have a complex model with FDTD. It can have a different 3D structure simulation, so it will have a multi-channel MRI coils. And this can have only with the frequency domain, but this can handle both time and frequency domain. And commercial version is demands always a bigger RAM. As 64 GB RAM is minimum. It's required for this tool, and this one is demands for a good processor. And one more comparison or as key features. So I like to compare between and not compare is just because they are working in the different sectors like ADS and AWS. ADS is having a huge market. They make hardware. They have got a good collaboration with Agilent and also Cadence. Cadence mainly deals with the VLS. It's a big industry, and it's having a specialty of signal integrity and power integrity, and it can make good thermal analysis for your circuits. And it is having all HFSS is started with HFSS, means it's a good analysis of your time domain, and the statistical design and sensitivity analysis can be made. Here this one AWS is fast growing and user friendly. It is having floating license and it deals with MMIC and LTC. It's advanced in upcoming technology where our circuits will be more smaller than what today we are looking, and it's having different products. It is having unified model, that means here it will be saved in a different kind of file sets, but this is having a single unified. And most of the researchers are contributing, like German, Chinese, and Japanese work with more with AWR. And we have got here with an iMatch, iFilters are intelligent wizards where ready-made circuits will be preparing for your design. If you are not having a good theoretical background of that device, but still you want to design, means it will support a lot here. And will have a good radar library, test wave, and 5G library. And these are my circuits. I started my career as an RF circuit designer with respect to a national instrument in Bangalore. So I was initially working with the model preparation. I used to write a code for the models for some of the tools like AWR. And later on in my research, I started designing some of the devices for radar application. This is one wideband low noise amplifier for radar application. This is ultra wideband for high precision radar, and this is an 15 gigahertz. Is for again it's for radar application, low pass filter. And this is one more a small radar for weather radar. We have prepared one pair of filters for diplexer application. And this is a single stage to make a small for an base station, ultra wideband LNA, and this is also one wideband LNA. This is a power amplifier which have a 40 watt output, and this one is not complete my contribution. I have designed only the matching circuit for the switch radar in one of the application. Rest are of complete my design. And in MMG, this is our small group. I'm working with sensor tile application and application specific balloons with filters I'm designing, and I'm designing microwave bridge for sensing application and sense per application. The one skin tissues there also I'm looking at what kind of a measurement we can do and what kind of RF circuits we can prepare for it. And in total summary, I like to say a few things. So since I work with numerous software tools, I like to recommend if someone is dealing with active devices, can go with MOM or X models, you can go with these two tools. And if you are looking with a strong electromagnetic simulations, you can go with an HFSS, where some accurate, and you can use FEM methods. And if you demand for a bigger RAM, and this one requires a good CPU, and it will go with FDTD. It will more advanced methods of 3D simulations. You can go with CST. And if you are looking with only coaxial cable wire connectors and radar cross section kind of a thing, you can use a FEKO tool. And if you are looking with an optical and electrical and thermal measurement with FDTD, you can go with the Lumerica. And there are either is a less expensive software. You can go with some, if your design is of planars, 2D structures with the filters, you can go with i3D. And this COMSOL, whenever you are having a mechanical specification and electrical structure, many measurements if you want to do with 2D analysis, COMSOL can support. And if you are end up with only the simulation model, you are not much interested to make a machine prototype, means you can just go with a LABVIEW, MATLAB founder. This makes a good numerical computational and scientific computations quite easy. You can make only simulation, it cannot make a good hardware. Yes, thank you. We'll start with that.